Next, chapter 3, control system components. I am representing DC servo motors, faculty Air Naik, HOD Electrical. The DC servo motor. Today now discussed regarding DC servo motors. These are constructed with permanent magnets which results into higher torque and inertia ratio and also higher operating frequencies. The DC servo motors can be again classified into three types. The DC servo motors in which the magnetic field is produced by a permanent magnet. Then magnetic flux is constant and it is called as permanent magnetic DC servo motors. The DC servo motors in which the output is controlled by the armature current is called as armature controlled DC servo motors. The DC servo motors in which armature current is maintained constant and the field is controlled by armature current is called as field controlled DC servo motors. But providing a constant current source is more difficult than providing constant voltage source. The time constants of field controlled DC motors is large than that of armature control because of requirement of constant armature current. Three types of construction employed in permanent magnet DC servo motors are shown below. First one is figure A, armature with slotted DC winding placed inside these slots. These are the magnet, this is the rotor, and this is the different slots. So slotted armature types. And figure B shows winding placed on armature to reduce high inertia accounted in figure A. This is the conductor bounded to rotating armature iron and rotating flux path. Figure C, winding placed on a non-magnetic cylinder which rotates in annual space between permanent magnet stator and stationary rotor. First one comes to armature controlled DC motors. This is circuit diagram. This one is armature resistance Ra, this is inductance value La, this is Ea input voltage, this one is armature current Ia, this is the back EMF of the motor represented by Eb. This is shaft of the rotor, rotating angle will be like this, and this is the constant the external fields. Ra is equal to armature resistance, La is the armature inductance, Ia is the armature current, If is the field current, Ea is equal to applied armature voltage, Eb is equal to back EMF, theta is equal to angular displacement of the motor shaft, T is equal to torque by the motor, equivalent moment of inertia of the motor, and load referred to motor shaft kg per meter squares. B is equal to equivalent viscous friction coefficient Newton meter per radian per second. The torque is proportional to the product of armature current and flux in air gap. Also flux is directly proportional to field current. Phi is equal to K1 If. By convention, phi is used for flux and psi is used for flux linkages. T is equal to torque is equal to K2 Ia into phi, that is equal to K1 K2 Ia If phi. That means T is equal to K into Ia. When armature is rotating, voltage proportional to product of flux and angular velocity is induced in armature, but flux is constant. Theta B is equal to K4 d theta by dt. Eb is equal to back EMF, K4 is equal to Kb is equal to back EMF constant. The differential equation for armature circuit is La di by dt plus Ra Ia plus Eb is equal to Ea, equation number 2. The torque equation can be given T is equal to J d square theta by dt square plus B d theta by dt plus K into Ia, equation number 3. By taking the Laplace transform of the above equations 1, 2, 3, then block diagram can be constructed as shown below. This is E0s, this is theta s. This is summing point. This one is the first block 1 by La S and Ra. This is the output of the block Ia into S. This is K Ts. This is 1 by S all into Gs plus B. Output is theta s. This is the feedback path negative. that is KBS into EBS. It reveals armature control for servo motor is a feedback system. Effect of feedback back EMF is the feedback systems. Back EMF increases the effective damping of a systems. The transfer function is given as theta s by EAS is equal to K by S all into LA J square plus LAB plus RAJS plus RA into B plus K into KB. Make them equation number 4. It reveals 1 by S term indicates system possesses integrating property. The time constant of the motor is smaller for smaller RA and smaller J. If LA is small and neglected, then transfer function becomes theta S by EAS is equal to KB by S whole into TS plus 1, where KS is equal to K by RAB plus K into KB, that is equal to motor gain constant is equal to K by RA common B plus K KB by RA. TS is equal to J RA by RAB plus K KB is equal to motor time constant is equal to J by B plus KT KB by RA. With small j RA reduced, the motor time constant approaches 0 and motor acts as an ideal integrator. The field control DC motor is shown in figure below. This is the resistance, this is the inductance LF, this is the external field, and this is the armature circuit. The shaft is connected here, rotating angle is theta, and this is armature current I is constant. So this ES 1 by LF plus RF IF into S, K2 by S whole into JS plus B, output is theta S. In this system, RF is equal to field winding resistance, LF is equal to field winding inductance, E is equal to field control voltage, IF is equal to field currents, Tm is equal to torque developed by the motor, J is equal to equivalent moment of inertia of the motor, and load referred to motor shaft. B is equal to equivalent viscous friction coefficient of motor, and load referred to motor shaft. Newton meter by radian per second. Theta is equal to angular displacement of the motor shaft in a radian. In the field control motor, the armature current is fed from a constant current source. Therefore, Tm is equal to K1 Kf If Ia is equal to K1 into Tf, where K1 is a constant. The equation of the field is LF dIf by dt plus Ra into Ia is equal to 0. The torque equation is J theta square d square theta by dt square plus B d theta by dt is equal to Tm, that is equal to Kr into If. Equation number 7. Taking Laplace transform of equation number 6 and 7, assuming initial conditions at 0, we will get LFS plus RF IFS is equal to S. Second equation, J square Bs theta S Tms is equal to Kr dash If into S. From the above equation, the transfer function of the motor is obtained as theta S by S is equal to Kr by S whole into LFS plus RF Js plus B, that is equal to Km by S whole into tau by S plus A into tau Ms S plus 1, Km by S whole into 1 plus S tau 1 into 1 minus S tau M, where Km is equal to Kr dash by RF B, that is equal to motor gain constant. Tau F is equal to LF by RF is equal to time constant of field current, and